All right, let's dive right into this Haskell refactoring explainer. Today, we're unpacking a genuinely elegant piece of problem solving based on developer Ang's recent journal entry. So, Ang was working on a console application, specifically zeroing in on a feature that converts Chinese text into numerical digits. Now, refactoring is something we all do, right? But what makes this particular journal entry so captivating is how it challenges a really common programming assumption, the idea that clear, explicit code is always the best code. We are going to look at how a surprisingly simple mathematical trick can completely overhaul a function's performance.
Here is the exact dilemma straight from the source. Ang writes, even though the code is rather readable, there are still rooms for improvement. This is a fantastic hook, honestly, because it sets up our entire journey today. We're looking at code that maps standard ASCII digits over to their full-width equivalents for this Chinese text conversion. The original code did exactly what it was supposed to do, and pretty much any developer could read it and understand it instantly. But, as you'll see, perfectly readable code isn't always the most efficient code, especially when you're trying to scale an application. Section 1. A readable starting point. The tedium of case matching. Okay, let's set the stage by looking at how this conversion was initially handled, and why it felt so safe, yet ultimately proved so inefficient. Take a look at this list. This represents the original function. It used 10 distinct pattern matching cases. It literally went down the line: if the character is a standard 0, map it to a full width 0. If it's a 1, map it to a full width 1. If 2, then 2. All the way up to 9, with a final fallback just returning the original character if it wasn't a number. Think about the tedium of this. This old case matching approach is a lot like exhaustively looking up every single number in a physical dictionary. You have to scan the entries one by one to find your match. It's explicitly clear, sure, but mechanically, it's a really bulky way to process data. Moving on to Section 2, the Unicode offset hack, math over literal matches. This brings us to the real aha moment of our refactoring journey. This is where Ang completely rethinks the problem, stepping away from manual lookups and stepping straight into the realm of mathematics. Instead of matching literal cases one by one, Ang realized we can leverage the contiguous, sequential nature of how these characters are stored in the Unicode standard. Because the standard ASCII digits 0 through 9 and the full-width digits 0 through 9 are stored in exact, uninterrupted sequences, we don't actually need a dictionary. We can just use math. Think of this contiguous nature like a mathematical ruler. Instead of searching for a specific notch, we can just slide down the ruler a set, precise distance to find exactly what we need every single time.
So the crucial point is this specific hexadecimal number right here, 0x-phi0. Ang points out that the standard ASCII character for 0 is located at the code point 0x0030. Well, by applying a bitwise offset, literally just adding this exact offset of 0x-phi0, it perfectly lands on the exact code point for the full width 0. And because both sets of numbers are contiguous, this single mathematical operation works for 1, 2, 3, all the way to 9. One single calculation replaces 10 whole lines of manual pattern matching. It is incredibly elegant. And you can really see the visual difference in the code base here. On one side, you have the bulky, explicit dictionary method with its long list of literal case matches. Then, on the other side, we have our sleek, mathematical ruler method. Ang introduced a new function using a mapping tool and that single offset of 0x-phi0. The code footprint just shrinks drastically. It's doing the exact same job, mapping ASCII to full width, but it's doing it with mathematical precision rather than brute force matching.
Section 3. Eliminating data conversion overhead, smarter data typing in Haskell.
The math was only half the battle, though. Let's look at the hidden tax exposed in this pipeline comparison. The old setup was secretly exhausting the system. To process the characters individually, the old code was constantly converting the text type down to a standard string, which in Haskell is a list of characters, mapping over that list, then converting it back to a string, and finally packing it back into text. That is a massive amount of overhead. Ang's new pipeline fixes this entirely. By using the new offset logic and a direct mapping function, the code completely avoids handling characters individually in a list. It just maps directly over the text type. Text goes in, text comes out. No back and forth conversion tax. This significantly reduces the overhead and drastically improves the efficiency of the application. Which brings us to Section 4, efficiency over explicit readability, the developer's trade-off.
As we wrap up this refactoring journey, we really need to step back and look at the philosophical takeaway Ang leaves us with. This is the core lesson of the whole explainer.
Eng openly admits that leveraging the contiguous nature of Unicode absolutely impacts readability. I mean, a junior developer looking at 0x phi 0 might not immediately know what that means, compared to seeing a 0 map to a full width 0. But, as Eng notes, we traded that explicit readability for faster conversion and far higher scalability. By removing the literal cases and cutting out the massive data conversion overhead, the application is just vastly more efficient. It's a calculated trade-off that pretty much every developer has to weigh when optimizing an app.
Which leaves us with this final thought. Think about your own projects for a second. Are there places in your codebase where you're relying on highly readable but incredibly bulky case matches or data conversions? Could a simple mathematical offset, or maybe just a smarter understanding of how your data structures are laid out, save you processing power? It really begs the question, when should scalability overrule readability in your code? It's a fascinating balance to strike. Thanks for joining me on this explainer, and I highly encourage you to view your own code through this mathematical lens today.